The section 3 of the chapter 1 is about bulk modulus. First, let me explain what is bulk modulus. If we compress a body, the pressure in the body always increases. The pressure increase, delta V, should be proportional to the relative volume decrease minus delta V over V in the cases of the infinite compression. Then the bulk modulus K is defined as the minus pressure derivative of pressure, the derivative of pressure with respect to relative volume, which is equal to minus the derivative of pressure with respect to natural logarithm V, equation 1.3.1. The bulk modulus K is the rate of pressure increase to the relative volume decrease, as I explained, and it is the index of how difficult the matter is to compress by pressure, P. If the compression is linear, the bulk modulus K is a pressure necessary to make the volume of the body zero. This diagram explains this point. This diagram shows the pressure, normalized pressure, relative with respect to the relative volume. The vertical axis is normalized pressure by the bulk modulus K. Vertical horizontal axis, upper horizontal axis is the relative volume V over V0. V0 is volume at zero pressure. Therefore, at one point at unity, the pressure is zero, and here pressure is zero. Volume is zero. The lower horizontal axis shows the relative volume decrease, delta V over V0. The left side is zero, no compression, no volume decrease, and in the right side, relative volume decrease is minus 1, namely the volume is zero. And this red curve shows the real compression curve of the condensed matter. The relative pressure rapidly increases with decreasing of relative volume or with increasing the volume decrease. If we extrapolate this compression curve at the zero pressure linearly, the bulk modulus K is found at the right side of this diagram, namely the relative volume as 0 or a relative volume decrease of minus 1. If the matter is compressed by the pressure P, volume V of the matter decreases, which does the work W to the matter. As a result, the internal energy of the matter E increases by the work W. In the case that the increase in the internal energy E is released from the matter by thermal conduction to keep temperature T constant, the bulk modulus in this situation is referred to as isothermal bulk modulus KT, which is defined as minus V times the partial derivative of pressure with respect to the volume V at constant temperature T, equation 1.3.2. This is the bulk modulus in a slow process. More typically, in the case of static compression. Let me consider the other extreme case, which is the case that the work W is completely stored as the enthalpy H in the matter. Namely, the process is too fast to release heat by thermal conduction. The typical situation is the elastic wave. The bulk modulus in such situation is referred to as adiabatic bulk modulus Ks, which is defined as minus V times the partial derivative of the pressure with respect to the volume V at constant entropy S. Equation 1.3.3. Clearly, the temperature increases by compression and decreases by decompression. In general, the adiabatic bulk modulus is greater than the isothermal bulk modulus. Namely, the compression is hampered by or impeded by thermal expansion due to the temperature increase by the work W. Then our question is how much are the isothermal bulk modulus and adiabatic bulk modulus are different. Then let us derive the relations between the isothermal bulk modulus Kt and the adiabatic bulk modulus Ks. Obviously, the relation between the isothermal bulk modulus Kt and the adiabatic bulk modulus Ks is the relation between the partial derivative of pressure with respect to the volume V at constant temperature and that at constant entropy S. Let us consider that the pressure is the function of the volume V and the entropy S. Then the total differential of the pressure P is equal to the partial derivative of pressure P with respect to the volume V at constant entropy S times dV plus the partial derivative of the pressure P with respect to entropy S at constant volume times ds. Then from equation 1.3.4, the partial derivative of pressure with respect to volume at constant temperature T is the partial derivative of the pressure P with respect to the volume V at constant entropy S plus the partial derivative of the pressure P with respect to the entropy S at constant volume V times the partial derivative of the entropy S with respect to the volume V at constant temperature T. Then equation 1.3.5 is can be expressed by the two bulk moduli. By multiplying all terms by minus V, the minus V, the left side of the equation 1.3.5 becomes minus V times the partial derivative of the pressure P with respect to the volume V at constant temperature T is equal to minus V times the partial derivative of pressure P at constant volume V with respect to the volume V at constant entropy S minus V times the partial derivative of the pressure P with respect to the entropy S at constant volume V times the partial derivative of entropy S with respect to the volume V at constant temperature T. Thus, the isothermal bulk modulus Kt is equal to the adiabatic bulk modulus Ks minus V times round P over round S at constant V times round S over round V at constant T. Equation 1.3.6. Then next is we want to express the minus V round P round S at V times round S over round V at T is expressed by well-known quantities. Then we substituting one of the Maxwell's relations 1.1.24, the partial derivative of the entropy S with respect to the volume V at constant temperature T is equal to the partial derivative of the pressure P with respect to the temperature T at constant volume V into the equation 1.3.6 Kt equal Ks minus V round P round S at V times round S round V at T. We have the Kt, the isothermal bulk modulus Kt is equal to the adiabatic bulk modulus Ks minus V times round P over round S at V times the partial derivative of the pressure P with respect to the temperature T at constant volume V. To express this quantity round P over round T at V over equation 1.3.7 by well-known quantities, we use the chain rule 1.1.31, namely round y over round x at z is equal to minus round y over round z at x times round z over round x at y to the to this red term. Then round p over round t at v is equal to minus round p over round v at t times round v over round t at p, which is equal to 1 over v times round v over round t at p times minus v times round p over round v at t. Then the former factor is the thermal expansivity, and the latter factor is the isothermal bulk modulus. Therefore, which is equal, this factor is equal to alpha kt. Equation 1.3.8. Because we expressed this red factor by thermal expansion coefficient and the isothermal bulk modulus, next issue is this green term, a green factor, namely the partial derivative of the pressure with respect to the entropy S at constant volume V. We modify this factor by using two Maxwell's relations and chain rule 2 times. One of the Maxwell's relation we use here is the partial derivative of the pressure P with respect to the entropy S at constant volume V is equal to minus the partial derivative of temperature with respect to the volume V at constant entropy S. The other one is the partial derivative of the entropy S with respect to the volume V at constant temperature T is equal to the partial derivative of the pressure P with respect to the temperature T at constant volume V. Then the round P over round s at v is equal to minus round t over round v at s. Then by chain rule it is equal to round t over round s at constant v times round s over round v at constant t. Then by using the this Maxwell's equation, this red factor becomes this one. Round s over round v at t is equal to round p over round t at v. Therefore, this green factor become round t over round s at v times round p over round t at v. And we apply the chain rule once more again. This red term becomes minus round p over round v at t times round v over round t at p. Then this green term, green factor becomes minus round t over round s at v times round p over round v at t times round v over round t at p. Equation 1.3.9. Each factor of the round p over round s at v can be expressed using a non-physical properties. The round p over round s at v is equal to minus round t over round s at v round p over round v at t times round v over round t at p, and minus round t over round s at v is inverse of round s over round t at v, and by multiplying round s over round t at v by the temperature T, this denominator becomes the isochloric heat capacity Cv. The second factor, the round P over round V at T, becomes the isothermal bulk modulus Kt by multiplying minus V, and the round V over round T at P becomes thermal expansion coefficient alpha by multiplying by 1 over V. And because we have T in the denominator, we have a factor T out of this here. Then the round P over round S at V is equal to alpha KTT over CV. As we have already seen, round S over round V at T is equal to the thermal expansion coefficient alpha times the isothermal bulk modulus Kt. Therefore, the equation 1.3.6 Kt equal Ks minus V times round P over round S at V times round S over round V at T becomes Kt equal Ks minus V times alpha KTT over Cv times alpha Kt. Then which is equal to Ks minus alpha KTT over Cv T Kt. Equation 1.3.11. In the previous section, we have defined the thermodynamic Gruneisen parameter gamma Th, which is alpha Kt V over Cv. Using this parameter, the equation 1.3.11 kt equal ks minus alpha times alpha ktv over cv tkt becomes the isothermal bulk modulus kt is equal to the adiabatic bulk modulus ks minus alpha thermal expansion coefficient times the thermodynamic Grunheisen parameter gamma th, the temperature T times the isothermal bulk modulus kt. Then, which leads to the adiabatic bulk modulus ks is equal to 1 plus alpha gamma th t kt, equation 3.12. Because 1 and alpha and gamma th and t are all positive quantities, therefore ks is larger than kt. The equation 1.3.12 also suggests the kt, the isobaric heat capacity, the isothermal bulk modulus is a thermodynamically more essential quantity than the adiabatic bulk modulus ks, because the adiabatic bulk modulus ks is becomes larger than kt because the pressure caused by the thermal expansion by the work done by the compression at pressures. Equation 1.3.12 is similar to the formula for the heat capacity 1.2.12.22. Cp, the isobaric heat capacity, is equal to 1 plus alpha gamma T times as the isobaric heat capacity Cv. Namely, the ratio of the adiabatic heat capacity Ks over the the adiabatic bulk modulus Kt to the isothermal bulk modulus Kt is equal to the isobaric heat capacity Cp over isochoric heat capacity Cv is equal to 1 plus alpha gamma th, equation 1.3.13. Finally, let us see some examples of bulk moduli. This diagram shows the adiabatic and isothermal bulk moduli of Pericles and foresight at elevated temperature and ambient pressure P0. The red curve is the adiabatic bulk modulus of Pericles, and orange curve is the isothermal bulk modulus of Pericles. The blue curve is the adiabatic bulk modulus of foresight, and green curve is the isothermal bulk modulus of foresight. We can see that the bulk moduli of mantle minerals is several tens GPa or hundreds GPa. You can see the bulk moduli of Pericles and foresight are very different. So bulk modules are very different among different methods. This feature is a distinctive difference from the heat capacity, which are more or less the same at high temperatures. Bulk moduli decreases with increasing temperatures, and the adiabatic bulk modulus decreases more slowly than isothermal bulk modulus because of the factor 1 times 1 plus alpha gamma THT. As we have already discussed, the adiabatic bulk we have already discussed the isothermal bulk modulus is thermodynamically more essential, but the adiabatic bulk modulus can be more precisely measured than the isothermal bulk modulus thanks to the sound velocity measurement. So this is the end of the section 3 of the chapter 1 bulk modulus.